Hello, everybody. My name is Lee Chinitz. I'm the CTO here at Octoscope, and I'm the moderator for today's session. First of all, just thank you all for joining us. Let me get started. Before I get started, I'll just mention, again, we are Octoscope. We're a maker of wireless personal test beds. And we have been doing these tutorial sessions now for the last several months. This, I believe, is number 10. And as we'll show later, all of the information that we have given, all the sessions have been archived on our website. You can feel free to go back and view any of those if you didn't see them before, and view this one again if you really enjoy it. Our topic for today is Wi-Fi mesh. Our speaker is Janne Linkola, who is the Director of Product Marketing here at Octoscope. Janne has a very broad background in all aspects of Wi-Fi, including work at operators, as well as equipment manufacturers, and now at a testing company. I think it's Janne's work with the operators that has given him a strong interest in this topic of mesh. And he has done some really good work in terms of figuring out how the requirements that operators have for mesh devices can be tested in a personal test bed like the ones that we have at Octoscope. So he's going to walk you through a lot of what we hope is very interesting information to you today. We very much welcome your input and feedback. So I will mention that we do these sessions live, although we do archive them, but we do them live on purpose. We do enjoy the interaction. We think it really helps the session when people ask questions. So there's a whole crew of us that will be moderating, or at least watching the questions that they come in. We'll answer some of them just directly, but others we will open up for discussion with Janne. And so definitely feel free to put your questions into the chat window. You have a Q&A window. You can raise your hand. So there's a number of ways you can get at us, and we will keep watching for that. So with that, let me turn it over to Janne.
Thank you, Lee. So yes, today's session is about Wi-Fi mesh, a very hot topic currently for the last, say, 3 or 4 years. There has been a lot of activity in the space, but the technology actually has quite long roots. As with many other technologies, the roots are in the military. In the 1980s and 90s, the federal government in USA put quite a bit of research dollars into researching how personnel, vehicles, command posts, assets could form ad hoc networks wherever they happen to be, and how they could communicate resiliently. That technology started trickling down to the civilian life. My first exposure in this space was in the very early 2000s, when the industry started talking about smart cities. There was a very famous and very influential RFP that the city of Philadelphia issued in 2005, where they laid out a vision of blanketing essentially the entire city of Philadelphia with Wi-Fi, thus giving internet access to all the citizens of the city, and thus making the city a more productive and equal place to live in, I suppose. I don't believe that particular plan ever got built, but it inspired a lot of other cities to do the same. As a result, many ISPs started building networks like this. Very famously, Comcast actually built Philadelphia, as well as Cablevision built a similar very big network in the New York tri-state area. Simultaneously to this, of course, there was a lot of Wi-Fi deployment in the enterprise, driven by productivity needs in the office and universities, hospitals, what have you. Now, in the 2010s, venture capital money started flowing into a consumer sort of at-home version of this technology. Lots of startups got funded, one of them being Eero, that got picked up by Amazon a couple of years ago. Google put money into their version of mesh Wi-Fi. And more recently, the ISPs have really started being active in this space. The last we counted, there are, out of the top 30 ISPs in the United States, I believe about 25 have launched some version of mesh Wi-Fi already. And these deployments are accelerating. Now, at the same time, various kinds of standards and technology specifications have evolved. There's specifications from IEEE, 802.11s, being the first one that just defined the mesh protocol in between nodes. Then they came up with 802.11k, V, and R, addressing various management and steering aspects, as well as R being the fast roaming standard. In 2018, Wi-Fi Alliance published something, that a certification program that they call Easy Mesh. This is another attempt at specifying the interface in between mesh nodes for vendor interoperability. Has moderate success. The last I checked, I think there are 30 devices that have certification, mostly in the ISP mesh side of the space. Just to further illustrate how hot this market is, here are some images that I grabbed last night from Amazon. There are really lots and lots of products in this space. On the retail side, sort of direct to consumer space, most of these products come in packets of 2 or 3 nodes, mostly 3. Now, notably, the ISP market is quite different. The most typical deployment of mesh in Wi-Fi or an extender in Wi-Fi is really only one unit. And I'd say about 95% of the deployments have only one extender in there. Now, why is this all happening? Well, of course, it's about coverage, right? Consumers and employees really demand good coverage, great internet access speeds, and for that, we just need to build a lot of Wi-Fi access points. There is a sort of an issue with Wi-Fi that people call the bad apple phenomenon that's important to understand in this context. And that is that while Wi-Fi achieves very high speeds when you're close to the access point, and while Wi-Fi also delivers pretty nice coverage, I mean, you can cover an entire house with Wi-Fi, you don't get those two things simultaneously, right? The coverage is achieved by very aggressive rate adaptation on the physical layer. In fact, there is 3 orders of magnitude of rate adaptation. So what that means is that a station at the edge of the coverage might be using 1,000 times more airtime for the same service as a station closer to the access point. So these stations are called bad apples. We don't want them around. It's not okay to only have 90% of stations in good coverage, because if 10% are in bad coverage, they are bad apples and they destroy pretty much the service for all stations. So that's another reason why we need good coverage. Anyway, today's session is going to be very demo oriented. The first demo that we're going to do is basically a variant of test that I think most of us are familiar with, rate versus range. In this variant, what we're going to do is simulate movement from an access point, a kind of a root access point, radially away from it towards the direction of an extender, and then beyond. And hopefully what we will see is the starting of a typical rate versus range curve where we're getting great speeds when we're close to the access point. And then as we move further away, we're going to see a decrease in the throughput. But as we are handed over to the extender, hopefully we'll see a bump in the performance and also a range extension further away. We will be performing the demo in the Stack Max system from Octoscope. It looks like this thing here on the left. As I said, we have a 2-node mesh set up in there. The root node is on the top chamber, and the extender is set up in one of the smaller chambers here below. We're going to be using the Octoscope StayPal product as the station. Remember, this is our test instrument that can simulate lots of different kinds of stations. And we're going to be doing the demo completely manually by essentially manipulating two attenuators here as we go. So anyway, let's jump onto the demo. So what we're looking at here is the Octoscope Ui. Many of you are familiar with this. I'm going to start some traffic here, and we're going to start the test from a point where the StayPal, the station, is connected to the root. Now, this particular mesh can deliver about 600 megabits per second. As you can see, we're at an RSSI here. The StayPal is experiencing an RSSI of roughly neg 40, maybe neg 38, and we're at a PHY rate of over 800 megabits per second. This is StayPal is a 2x2 device, but the mesh under test here is an AC mesh only. And as you can see, the root attenuator is set to 0, so we're very close to the root, and the extender is set to 90, so we are quite far away from it. So let's start moving towards the extender. So basically, we're going to start decreasing the attenuation towards the extender, increase the attenuation towards the root. As you can see, our RSSI is going down. We added 12 dB, so correspondingly, we went from neg 38 to neg 50. The PHY rate hasn't adapted yet. We're still at the good throughputs here. We're going to move close to the extender, add attenuation to the root, simulating movement further away. So RSSI is reacting. Let's add a little bit of more through attenuation. So we're starting to now see some PHY rate adaptations. Now we're at speeds of roughly 400 megabits per second. Make this a little quicker. Now, as you can see, I'm adding more attenuation towards the root node, and as you can see, we're going down on throughput quite a bit. We are now at close to 100 megabits per second here. Our RSSI was roughly neg 80, and there you go. Here we see a roaming event to the extender. As you can see, the extender attenuator is set to 0. We're very close to the extender. The root attenuator is set to 90. There's no way we can be connected to the root. We're at neg 40 RSSI. So therefore, we are very close. We must be connected to the extender. Now, interestingly, our throughput is only 300 megabits per second here. Now, I should say that the root node and the mesh node that we're using here, they are identical hardware-wise. So why are we getting only half the throughput from the extender? Well, this particular extender model happens to be a dual band extender, and it's serving the station with the same chipset that it's performing the backhauling. So every packet in this test gets sent twice by that radio. So therefore, we can only get half the speed. So that's why we're seeing half the speed from the extender compared to the root. So anyway, let's move further away from the extender. We should see RSSI going down, and speed going down at some point. So now we're quite far away, and this is basically the range benefit that we were looking for in that demo. Let's see if we can move the station back to the root. Let's move closer to the root here. Add some attenuation to the extender. Let's see if we can see it back to. All right, and there you go. This is now a handover back to the root. As you can see, we're back at neg 40, and the throughput is closer to 600 megabits per second. So this can only be achieved through the root node. So there you go. A live demonstration of roaming and steering in a mesh. Now, how do I know steering really happened? Well, I took a trace in our practice run yesterday. Here is that trace. As we can see, the mesh is really issuing BSS transition management requests. It's giving a BSS ID candidate here. The station takes about, 200 milliseconds to react to that. It sends a response to the steering root node and starts authentication and reassociation process with the target BSSI. So it in fact was really a 802.11b steer that our StayPal reacted in about 200 milliseconds. Let's see. Am I seeing some questions so far?
We have one person who's wondering about the antenna specs of the DUT in the current demo. So I had actually tried to clarify if this is a question about the mesh product, and the response was no specs of the DUT, but the DUT is in fact the mesh product. So I guess this question is asking about antenna specifications for the DUT. I don't know if there's anything you feel like you want to say about that.
Yeah, it's the product. We're not, we're trying to be vendor neutral, so we don't promote or discourage any products here. This particular mesh product happens to be working very well. I think it's like a mid-power style product with I think a 3 to 6 dB antenna. It's built in. It's a relatively low-end product, as I mentioned. It's a year or two old as well. Anyway, I think the demo, as you already saw, going through an extender does come at a cost, right? It's not free to use the extender. The number one thing is that every packet gets sent twice. If the extender uses wireless backhaul, then that's sending packets twice over the radio interface. As we saw with this particular design, where the chipset is serving the station as well as doing the backhaul on the same chip, that has an impact. That halves the speed. I mean, we can only ever from this product get half the speed from the extender as we would be able to get from the root. Now we're also doubly exposed to any interference and congestion in the environment, right? Everything gets sent twice, so any kind of interference we expose ourselves doubly to. Now we also create a lot of congestion. Every packet gets sent twice, so if you're an ISP covering a lot of homes in a particular neighborhood, you should be worried about that. And of course, the handovers themselves, while this particular steering event only took a couple hundred milliseconds, 200 milliseconds is not nothing, right? You would notice something like that, certainly in a Wi-Fi phone call or even maybe a Zoom session like this. So really, the station should use the extender only when it absolutely has to. When we can verify that the extender would provide a better service. Well, how's the station going to know that? It turns out this is a very complicated problem in Wi-Fi. This really is the root at why we need to test these systems so well. And the issue sort of starts with the design of how Wi-Fi was designed to begin with, right? The mobility management, the decision to roam, is a feature of the station in Wi-Fi. Cellular networks work differently, right? In cellular networks, it's the network who decides where you need to go. So if you think about this mobility problem from the station's point of view, it's quite tricky to know where to connect to, right? In a mesh like the one that we just tested, only one of the nodes is connected to the internet. It may have a different radio than the extender, but let's just say it has a similar radio. Now, the extender may only be able to deliver half the speed that the root can. There's also congestion, loading in the environment. These are difficult things for the station to know. Now, Wi-Fi has some technologies, namely 802.11k, V and R, to make some sense of this situation. But it turns out that the mesh products out there use also a lot of proprietary techniques to figure this stuff out. And certainly with stations that adhere to the V standard very well, these stations are easier to steer and easier to connect to the right node. But anyway, I mentioned that there's going to be a lot of demonstrations here, so let's do the second one. This really is going to be quite cool. We are demonstrating for the first time live something that we've recently developed here at Octoscope that we call field to lab replay. Essentially, this technology allows us to go into an environment of interest, let's call it a house or an office or even an open air environment, and capture the propagation characteristics that are prevalent in that environment. And we can then take that capture and replay it on the Octoscope testbed. And we can subject devices such as access points, mesh networks, or stations under different kind of tests in that environment. From the station's point of view, it's as if we were in that house that we captured the propagation characteristics of. They don't really know any difference. So to sort of illustrate, we're doing a demo here, and what we did earlier this week is we went to a 2-story house here in the Boston area. Looks a little bit like this. The house had a basement, and we set up a 3-node mesh in this home. The root node, the one that's connected to the internet, we set that in the basement. And then we had an extender on both of the floors. And we used also a recently launched product that we've just launched called the Field Pal to capture the propagation environment. Now, the Field Pal can do a lot of things, but one of the things it can do is it can make these on-site measurements. So what we did is we captured a walk inside this house. We started in the basement in one corner of the house. We walked through the basement, through the stairs to the first floor, did a little tour on the first floor, again took the stairs, went to the second floor, and walked to the opposite corner of the house on the second floor. Now, what we captured looks a little bit like this. So this is the walk from the basement to the second floor. These are we're illustrating this measurement now as in form of an Rssi measurement across time. As you can see here in the beginning of the walk, when we're in the basement, the root node is the most dominant. As we enter the first floor, the extender on that floor has the strongest signal. And as we enter the second floor, the extender on the second floor is now the node with the highest signal. Now, we're going to be demonstrating this capture with a 2-node system, just like the manual demo. So we have the root node here on the top chamber, the extender corresponding now to the extender on the first floor in that house. We have here in this chamber, again, we're using the same exact station that we used in the previous demo, but now the difference is that we use these measurements, the green curve, to drive the attenuator connecting the station to the root. And we use the measured gray curve to drive the attenuator between the station and the extender. We do these completely synchronized, just as captured in the environment. So this, from the station's point of view, this is the exact equivalent of making that walk inside that house. And it's actually the same thing for the mesh as well. So let's see how that goes. I will be starting a couple of scripts here. And I have this test is going to be taking 4 minutes, so we're going to be taking this slowly. As you see, we start at 600 megabits per second here, so this means that we are connected to the root in the basement. And soon the attenuators should start kick in. Here we go. The attenuator towards the root node is increasing, and we see a corresponding dip on the throughput as well as the phi rates. we are taking a slow tour here in the basement, so just bear with us. Soon we will enter. I think now we are at the stairs in between the basement and the first floor. Now we are on the first floor. As we just saw, we walked past the extender on the first floor. Notice how we only got 300 megabits during that time, so it means that we were connected to the extender. Here's where the handover happened, basically. Now, we are walking further in on the first floor, and we'll be soon hitting the second floor here. And let's see what kind of throughput dips we might be getting, since the extender on the first floor will be relatively far away. Okay, it looks like we might have just passed the lowest point here, or I'm wondering if we're coming to that. It looks like we're coming into that now.
Hey, while you're watching it, maybe you
sure.
want to take a question.
Yeah, of course. Yeah, this is another 2 minutes, and it's pretty boring. So
okay, this one came in on the chat. Does the recording of the home have any scaling issues with the instruments, given the ADC and FEM of the instrument towards lower SNR to be considered? So let's see. I think the question is, I'm not sure what the end part of that means. I don't know, Naveen, if you want to raise your hand, we can unmute you, you can ask it. But I think the question is, will there be some sort of bias in terms of your measurement of the path losses based on the measuring instruments themselves?
So we have basically calibrated that out, hopefully. We've taken into account the measurement instrument, as well as the instruments emitting the signal here. So that we end up with just the path loss being the thing that was measured. And so in this way, this becomes independent of the measurement device, as well as of the access points being used. We end up with the path loss, and then we can apply this path loss profile to any basically any device under test. And if we use other stays for the test, then we would have to calibrate it a little bit, but it's a relatively simple calibration. All right, here we go. So this is the full walk. We're looking at the plot here on PowerPoint of the same measurement that we just looked at. So this is the throughput that we just saw. We were served by the root node here in the beginning of the walk, and we performed the walk forwards to the second floor, and then backwards back to the basement. So we get great throughput here in the beginning and the end, because we are served by the root node. And here in the middle, we were served by the extender on the first floor. And as you can see, we saw a little dip here when we were on the second floor at the furthest corner. The extender couldn't quite reach that. So that's pretty cool.
Sorry, sorry. So question going on here. So the question is, if we don't share the front hall and the back hall, then would we see a flat line? And I think the next part is just a clarification. If there are two radios, would the transition be smooth?
These are excellent questions. I think the first, if we have a tri-band situation where we don't share the same radio for the front hall and back hall, then certainly we would see something much more flatter. In fact, if we had an Ethernet-based back hall from the extender to the root, then I would say the line would be almost flat. Now, there is, of course, that couple hundred milliseconds of gap, and we will see some sort of a dip like this, but it would be smoother.
We've got a couple questions going, so why don't we just take those right now? How do we get the RSSI before and after the handover event along with the BSSID details and handover speeds? Is it from packet captures that look similar to Wireshark captures?
Yeah, so let me maybe first take the RSSI aspect of it. So as you noticed, we were using the Octoscope StayPal test instrument. So as long as we're using our own test instruments, we get very rich KPIs from those, RSSI being one. That's what we were plotting there on the real-time user interface. Now, if we were interested, and we would certainly be interested in the handover time, we were using V there and not R, but we'd be able to. So we have a test cases that basically use packet captures to notice when the messages are issued and then when the handover is complete. So that kind of real-time plot, we only see a dot on that plot once a second. So this type of plotting technique is not really adequate for analyzing millisecond level events.
And then there's a similar or related question, which from David Herman asking, does the StayPal support KVNR?
It supports K and V. I personally I'm not entirely sure if it supports R. Do you happen to remember that? I haven't tested R on it. The thing, the R is kind of rare, especially in the consumer side of the business, right? It's certainly used in the enterprise space, but we have a lot of consumer side customers. So I think we'll have to take that question and answer later on. But I know K and V are supported, and it's the StayPal has a very nice V implementation. We'll talk later about sort of various interop issues that there are in V, and our implementation happens to be one of these easy ones. So let's move on. So this is the throughput plot that we were just looking at. Now, a question that you might ask is, well, is this good? Is this optimal behavior? Turns out this is a question that's quite easy to answer with our field to lab replay technology. What you're looking at here is a superimposed image of two different plots. We essentially performed that same test that we just looked at, but what we did is we locked our StayPal first with the root node only, and the green curve is the throughput that we got from the root node. As you can see, we've got great speeds here in the beginning and the end, but essentially almost no internet access here when we were on the second floor. Now the gray curve is the same exact walk, but now we locked the StayPal onto the extender on the first floor. So as you can see, we did get some throughput from the basement. Now, obviously, root was a lot better, but the extender was the dominant technology here in the middle. And what we can do is we can combine these two graphs and basically take the highest value at any given moment, and we get this thick curve here, right? This would be let's call it the highest achievable speed, or let's call it the ideal performance along this walk path. And what we can do is we can compare the orange curve to the ideal curve, or the highest achievable curve, and this is what we see. So as you can see, actually this particular mesh system delivers almost the ideal speed at all times. There are a couple of deviations. Number one, there are two of these handover events as we get handed over from the root to the extender and back. There's a little dip here in the performance because of that. And then interestingly, here on the first floor, there's a section of the first floor that is actually better served by the node in the basement. It's the area that's just above the root node. So we would have been better served if the mesh had steered us to the root node. Now it didn't do that. I'm assuming because the benefit wasn't that great, right? The deviation is only about 50 megabits per second here, so pretty good. Now the beauty of the Octoscope test system and this field to lab replay technology is that we can run all sorts of variants of the same test. So here is a 3-node variant of the same thing. So this is the maximum achievable speed that this system could deliver along this walk path. So what I basically did is I added the blue curve here, now corresponding to the speed that the extender on the second floor would deliver if we were only connected to that. And interestingly, as you can see, the extender on the second floor in the location that it's at actually works a little bit better than the extender on the first floor. The maximum speed is, for the most part, achievable either through the root or the extender on the second floor. There are a couple of these sections where the gray curve is the dominant, but really, you know, if you were to place extenders in this house, you would probably want to actually put it on the second floor. Now we can then replay a variant of the automatic demo that I just showed. So we can set up a 3-node system on the Octoscope testbed. You know, root node again here in the top chamber, and the 2 extenders in the smaller chambers, and we can use the attenuator profiles corresponding to the 3 measurements that we performed at the house to drive synchronously these 3 attenuators, and we will achieve a virtual walk through the house. And in fact, we did that. And this is the throughput that we got. So the throughput walk from the basement to the second floor and back with a system that now has 3 nodes. And we can compare that to the ideal. This is that comparison. So notice again, we have a handover event here, a little deviation from the ideal. We have interesting 2 dips here in the middle, kind of symmetrically around the point of the furthest location here on the second floor. I mean, I haven't looked at the trace, but I'm guessing these are maybe some kind of handover events. But the really interesting aspect of this whole thing is this region here on the right. So as we were performing a virtual walk back to the basement, the mesh took quite a long time before it steered us to the root node. I don't know why. You know, of course, we could take traces, with our synchro sniffing technology, and start analyzing this. But if I was the tester for this system, I would say this looks like a bug to me. You know, it took basically, the root node was clearly the best node here for about at least 20 seconds, maybe 25 seconds, and it took quite a long time for the mesh to recognize that. So, so I would submit that to the vendor. If they agree that that was a bug, and if they deliver some new firmware to me that is alleged to fix this bug, then it would be the world's easiest thing to replay this test. It would take 240 seconds essentially to see if we now still see this deviation, or whether the orange curve is now closer to the ideal curve.
Hey, Janne.
Yeah.
So you do have a question. I figure you may want to talk about this one a little bit. The question is, was the survey capture manually imported into the test bed, or is it done by somehow importing the survey file into the test bed itself? Maybe you want to talk about the actual process for converting the field PAL measurements into the attenuation settings.
Right. Yeah. So the technology is relatively new, and so we're still working on some of the finalizing touches of that. But it's envisaged as a completely automatic process. So you essentially you go to the field, you use the field PAL to capture the environment, and then you have tools available to you. You essentially import that into the octoBox system, and then just basically choose what kind of walk you want to perform, right? We can perform, and what kind of a configuration you want to expose to that walk, right? Whether it's a single node, 2-node, 3-node, we can change the walk speed, we can change the direction, we can add stops. We can go forward, stop for 10 seconds, go back. There's infinite variance in how the system can be replayed, and the process is going to be automated and hopefully easy to use. All right.
We have a raised hand.
Sure.
Question? I have two questions. The first one is just now you demonstrate the effect of roaming, but how about the band steering? So from steering from 2.4 gig to 5 gig, does it can test validate such scenario? This is my first question. And the second one is, does the octoscope does octoscope simulate the some mesh protocol behaviors, such as easy mesh or .11s, or some even some proprietary mesh solution, or these test devices as not relative to any mesh protocols?
All right. Clear enough. Let me address the first question first. So just to play back, you're asking, well, we saw AP steering here. Can we essentially test band steering? Well, from a V message point of view, it's the same exact message. It's a different BSSID. The steering AP just gives its own 2.4 gigahertz version of the BSSID. So from our point of view, it's the same exact test. We did not in this test that we just saw, the mesh quite possibly could have been performing band steering to create, perhaps coverage benefits. We would have been able to measure the impacts of that. Maybe these little dips are in fact band steering. I don't know. I haven't looked into it, but maybe that's a great way to go start addressing your second question. So you asked whether whether we simulate these mesh protocols themselves, or whether we are more just an environment. We are not a network simulator on our own. I mean, we do have golden test instruments. One called the StayPal, which is our golden test instrument that can be used to simulate many kinds of different stations. And we have a golden access point that we call PAL6 that can be used as an access point for testing, but they don't support Easy Mesh or 802.11s. We would consider, if those are things that you want to test, then these would be attributes of the device under test. The mesh that we saw there could quite possibly be using 802.11s or Easy Mesh in the background. We don't really know. We didn't look at that particular thing. But so essentially, what the Octoscope system is, we can create an environment for you to take any Wi-Fi product into, and then we can characterize the performance of that product while giving a rich set of KPIs and traces and things of that sort while performing those tests. But we are not a protocol simulator,
okay.
if that's what you're looking for.
Thank you very much.
Makes sense? All right. So what we've been looking at here is a field-to-lab replay technique for testing Wi-Fi. It's very, very useful technology for all sorts of test cases, especially for mesh, because with mesh, the test scenarios become quite complicated very quickly. And a lot of people are more comfortable testing meshes in a test house. So with this kind of technology, though, we can replicate the user experience just as captured in a test house, and we're able to replay it in the test bed. So this will greatly speed up any kind of testing efforts. And also we get repeatability and reproducibility that you would never get test house. Now, having said that, there are other ways to test mesh. One approach is to follow performance standards. Previously, we had a seminar on the Broadband Forum TR398 effort. We addressed their first issue that they call issue 1. They are now working on an issue 2 that's I think is going to be out shortly. And this new version will have some performance and roaming test cases for mesh. There is ongoing work in other industry bodies that we are participating in, Wi-Fi Alliance and Etsy, notably. These bodies are also working on performance test standards, and we assume these will cover mesh at some point as well. Just before we go into sort of final Q&A, let me just talk a little bit about the interop, since I promised earlier on. As I mentioned, there are quite a lot of interop issues with these steering techniques, many in V alone, outlining here a few. And then if you have to use steering with a device that doesn't support V, there are various legacy steering mechanisms but they have even more interop issues. So a thorough testing of steering behavior is an absolute must with any kind of mesh testing program. So with that, let's see if there's any more questions.
So we do. We have a question. They're asking, is there anything engaged with Wi-Fi 6 today?
Wi-Fi 6? Yes. So our test system supports Wi-Fi 6 fully, both from an RF point of view. Actually, we support 6E as well from an RF point of view. And both of our test instruments, the StayPal and the PAL6, are already Wi-Fi 6 compatible, or support Wi-Fi 6. The entire test bed is ready for Wi-Fi 6. 6E support, the new frequencies that FCC has now opened up. We will have support in our PAL6E test instrument early next year, and then the StayPal will probably support it a little bit later, maybe late first quarter.
Can the StayPal be configured so that instead of being locked to a specific channel or band, it would be able to roam? I believe the answer to that question is yes. I'm pretty sure that you can go into a regular scan mode like any other station.
You can lock it as well.
Yeah, you can lock it. And then there's just a final question, which might as well just talk about. Do you see any aspects of Wi-Fi 6 that the extenders can benefit from? So is there something specific to Wi-Fi 6 that I guess helps from a mesh protocol point of view? I'll take a little bit of a crack at this while you think about it. One of the things that Wi-Fi 6, has at least more kind of robustly than Wi-Fi 5 were things like 160 megahertz channels and 8-stream connections. We have heard from various operators that they would use, especially things like 8 streams, more as a backhaul technology than anything else. That is not focused on the front haul side, just obviously because it's going to be quite hard to get stations that support that many streams. But since you're building a mesh, you can do whatever you want. So just from a enhanced backhaul point of view, I'd say that's at least one aspect. Any other thoughts?
I can't think of. I mean, it's a major architecture of the Wi-Fi radio interfaces, as everybody knows. So it's going to benefit all sorts of usage scenarios, including mesh. But I can't think of anything specific that would address mesh in it. But yeah, the benefits will be highly seeable, I think.
Yeah, I think there are some, potentially even others, although we haven't heard, so much about this already. But I mean, you could imagine, a mesh system making use of OFDMA so that instead of serving, for example, instead of a root node serving different mesh extenders at different times, if it were possible, it could serve them simultaneously. I mean, that would be quite an enhancement, although probably a very specific use case. So I don't know if we're going to see that anytime in the near future, but there are definitely, you can imagine things that could help quite a bit.
Yeah, I would say that going back to that picture that I showed that talked about the difficulty in deciding which node to connect through. Wi-Fi 6 will certainly have a major impact into that decision, because of the new types of avenues available, right? Just the fact that we have now a very efficient technology available on 2.4 gigahertz, I think opens up some interesting techniques that one could take advantage of in a mesh. You could take stations that are maybe a little bit lower performing or don't require quite as much speed. You could maybe take and move them to 2.4 because the service is now better on 2.4 than it would have been in Wi-Fi 5 world. And so I think steering techniques will probably adapt greatly in Wi-Fi 6 world because the radio just operates so differently, and certainly BSS coloring will have an impact into tightly built networks, especially in the ISP context. You're oftentimes your own biggest self-interferer. So Wi-Fi 6 will have, and the BSS coloring feature will have an impact into how these products will work in the future.
And one more is two more. Is the new system available to customers already, or when will it be available? Not sure what the new system refers to, but maybe Yanni, you could just talk in general about.
Yeah, I think the question is probably about this field to lab replay technology. So yeah, so I would encourage you guys to talk through your sales contacts, but yeah, we'll be making this available very shortly.
And Thomas, hi Thomas, would like to know, will the Field Pal support Wi-Fi 6E?
A future version of Field Pal will. The current version that we're shipping today does not. Field Pal in many ways is similar to our Stay Pal product. It's essentially a Stay Pal in a different form factor. Well, there's a couple other differences, but sort of conceptually, and so it's sort of tied to our Stay Pal roadmap, which I mentioned would be sort of a late first quarter, maybe early second quarter next year type of time frame. So the current version of Field Pal only supports Wi-Fi 6, not 6E yet.
Okay, we appear to have cleared the questions for the moment. I don't know, Yanni, if you'd like to wrap up here, we can wait and see if there's any more questions that come in.
Yeah. So thank you. As always, we will be making this session available on YouTube, like all of the previous ones. As you can see here, we have 9 tutorials already, and thank you for attending, and thank you for the lively interaction.
Yep, I will. I'll echo that. Thanks everybody for attending. Thanks everyone for your questions. The YouTube link. There's a question about the YouTube link. Everything will be. There is no YouTube link currently. We haven't put it up yet. But if you go to our website, then you can get all of those links. And I don't know if one of the sales guys wants to speak up in China specifically. Are those links somewhere else?
Yeah, they will be on the Paralink website. So if you go to our partner's website, which is the partner in China is Paralink, they will have those videos located so that they're accessible via in China.
Okay. And yeah, so again, thank you all for your questions. And if you do have questions that occur to you, either website, could you write down here? Yep, we can do that. Chuck, could you handle that? Open question. Do you see it or not?
I do see it. The question about writing down the website, you mean?
Yeah.
Sure.
You could just put down
Paralink,
and then put ours in there just in case. But
we'll follow up with everybody. I'll make sure the information gets out there. Yeah, actually, I'll put that up there right now.
Okay. Right, but again, do follow up with your local contacts or with any of us, and we look forward to talking to you again in the next tutorial.
Great.
I'm going to leave this open just briefly while Chuck gets that information in there. All right, so yep, and obviously just in case it's not completely obvious, you can find the information on our site here. Previous videos linked to, and this one will be linked there. All right, thank you all, and
Thank you.
see you soon. Bye.